So the force field is a very good idea because it's computationally very inexpensive. You can consider very large systems, run simulations. We will talk about this later on for a very long time. Um, but the problem is that the force field which we use should be really good, of high quality, so that if the force field predicts, for instance, a particular geometry of the system as being a stable minimum of the total energy, very similar geometry, ideally exactly the same, would have been predicted by running, say, the density functional theory, or, or even more sophisticated technique. So the question arises as to how to create a force field um, which would be able to be trusted, to be able to reproduce the behavior of our system, how the energy changes of our system when atomic positions change, whether forces on atoms would be the same as you would obtain if you run, say, density functional calculations. This method should be simple, so it should be computationally inexpensive, it should be precise, it should give good results, and it should be versatile. We should be able to apply this method to a wide variety of atomic geometries. So the idea of such a method is quite popular right now, and it is under a roof of machine learning methods. It's called machine learning because the computer learns from the so-called training set. So suppose we have performed high quality density functional calculations on our system for a particular set of geometries. So we have two molecules, for instance, and we would like to calculate what the interaction energy between these molecules is. So we position these two molecules with respect to each other at a certain distance, and then calculate the DFT energy of that set of of these two molecules, and record this energy together with the forces acting on all atoms of our system. Then we shift one molecule with respect to the other a little bit, repeat the calculation. Then we probably rotate one molecule with respect to the other, repeat the calculation. And so we will position these two molecules with respect to each other at different positions. And this way, we will collect a set of data that for the given geometry of the whole system, we have the total energy and the forces acting on atoms. So this is the training set. So that means that for a particular input X, we would have certain outputs Y, and we would have a certain number, capital N, values of this position. So we have Xn, Yn for N up to capital N. So this is our training set. And the question arises, okay, once we're given this training set, can we create a function y of x based on this training set such that if we input into that function a particular geometry x which is outside the training set, we would get the value y. For example, a force acting on an atom, or the total energy of the system, which would be a very good approximation to the actual value. So the machine learning methods solve this problem using a probabilistic approach. So let's try to get an idea of this method. And we will start from a simple curve fitting problem. Suppose we choose a sinusoidal function, sine 2 pi x here, and let's create 10 points which would reproduce this sinusoidal function, but with some noise. And these points are shown by blue dots here. So there are exactly 10 points here. Okay, and we would like to reproduce this function with a polynomial of the order m. Yeah, so the highest power is m. So in other words, given these 10 points, so we know precisely the positions of these points x on the x-axis and their value y on the y-axis, we would like to choose these coefficients omega, which form a vector omega, such that if we choose another point x, which is outside this training set, we would have a very good prediction of this value of the y corresponding to this point. To solve this problem is quite known. It's deterministic, entirely deterministic, and it is called least square method. So what we do, we create an error function here. So we take this assumption of the analytical form of our function. In this case, it is a polynomial. Which depends on these parameters w, and we take a square of the differences of that function at the point xn and yn. So xn and yn are points of our training set, and we sum over all training points in the set. Of course, we would like this error to be the minimum possible, and this is a sum of the squares. So if you run an optimization problem for this function, you will only get a minimum. You cannot get a maximum. So we differentiate this function with respect to all these parameters omega, alpha, and we get a set of linear equations for them, which we can solve very easily on the computer. Right, and let's see what are the results. As a function of the number of points in this polynomial. So the training set in all cases is the same, 10 points, but we choose a different number of different power of our polynomial. If we choose a linear polynomial, so m is equal 1, so of course our function y would be a linear function, and if we run the least square method, we will get this function, which roughly goes through all the points, but it's a very, very bad set, a bad fit. If we take m equal 3, actually, we achieve a rather good fit through the points. Yeah, but still, in some places where the noise is large, we had quite a deviation from the actual function we're trying to reproduce, which is our green line here, the sinusoidal function. If we take m equal 9, with m equal 9, we have exactly 10 parameters. Remember, there's omega naught as well. And in this case, this system of equation becomes entirely deterministic. So we find our parameters such that this error becomes exactly equal to 0. We have exactly 10 points, and we have exactly 10 parameters, so we can ensure that every single point is reproduced precisely. And you can see from this graph that the red curve, which is our predictive function, goes through all these points precisely. So the error is 0. However, the function is absolutely horrible. The fitting is very, very bad. This is called overfitting problem. And in fact, in order to have this red function, our polynomial, to go through all these points exactly, it appears that these coefficients omega are very, very large. Some of them 10 to the power of 7. So with a small number of parameters, like in this case, we have a very bad fit. For a very large number of parameters, we again have a very bad fit. And somewhere in the middle, we may have a reasonable fit. Actually, if the data set we train our polynomial would contain many more than 10 points, as in this example here. So you see the number of blue points is really, really large. Then we have a perfect fit. So this method was deterministic, and we have this overfitting problem. So of course, in reality, we don't know, given the training set, how many parameters we need to take. We don't even know which analytical form of the function to take. So we need to try to understand where we done something wrong. Maybe our method has to be somehow modified. And we noticed that in this overfitting case, these coefficients omega become too large. So the first idea is to try to regularize this problem, to avoid very large values for the parameters omega. And for that to do, we can try to add to our least square method a penalty function, which contains squares of the parameters, sum of the squares of all the parameters w, omega, or w. So it's like a penalty for having large parameters. Of course, we have to introduce an additional parameter, lambda. Okay, let's see what will happen then. We minimize again this function with respect using least square method to find the best values of the parameters omega, but using this regularization term. And what happens with the polynomial order 9, for which before we had a very big problem, overfitting problem, now we have a rather reasonable fit, as you can see here with the red curve. However, this happened for some particular value of the lambda. Here on the right, you can see how the error actually depends on the choice of the lambda. And when lambda it is shown in logarithmic scale, here is rather small, but not too small, the error is reasonable. We have a Plato here. If you take this lambda too small, the error actually is reduced. If you take lambda very large, the error increases. However, if you run a test, so in other words, now you try some additional points of the sinusoidal function, which we didn't include in the training set, then you see the deviation in this case is rather significant for very, very small values of lambda and for very, very large values of lambda. And only in this region we have something reasonable. So this deterministic approach is actually not working really well because we have this problem of how to choose lambda, how to choose the parameters. So a way forward in this been to use a probabilistic approach, which would work for any training set, no matter whether this training set is rich, contains many points, or small, contains just a few points. So in the following, I will try to explain to you how this probabilistic approach works. And the first point is to introduce this so-called likelihood function. So what is this likelihood function? So again, we have points xn and yn, which corresponds to our training set for our function y of x. But this time, we create a probability distribution, so-called likelihood function, which is a product of Gaussian functions, and each Gaussian function is taken for one particular training point. So we have a product here over all training points. The capital N is the total number of training points we have. In our example, it is 10. And this Gaussian depends on sigma, the dispersion in the Gaussian function, which happens to be in the normalization and in the exponent. And it contains explicitly our function we would like to optimize, which contains these parameters omega. So in order to choose the best parameters, and this time we have omega and sigma at the same time, we have two types of parameters here, we would like to maximize this likelihood function to have a better match of our trial function y of x to the training set. And the simplest way of doing that, because we have a product of exponentials, is to calculate the logarithm of that likelihood function. And if you calculate the logarithm of that likelihood function, you will get this expression here. And because of the minus signs, the maximum value would be achieved if you minimize that expression with the plus signs. So this term does not depend on the w's. So maximizing this expression with respect to the w's would correspond to minimizing that expression, which is essentially the least square method. So minimizing that sum of the squares would give us the same expression for the w's as we had before, or omegas. I always mix this up, but you know what I mean. I mean these parameters are parameters. We also need to maximize that expression with respect to the sigma, and you can easily take a derivative of the expression with respect to the sigma. You will obtain for the sigma the following equation. So the least square method would give you these w's, and once you know the w's, you can substitute them in here and you get the value of the sigma. This would give you the likelihood function. And then you can say, okay, now I can predict, because this is what I want. I want to take a value of the x, which is outside the training set, and predict what would be the value of the y, right? So now we can take it as a Gaussian distribution. I will predict it with a certain probability based on that found value of the sigma from this formula and the values of the parameters from least square method. So it won't be deterministic anymore because we will predict with a certain probability, which we can set, say 90%. And we will do this at random. Okay. However, because the coefficients omega are found in this method via the least square root, we still can't avoid having very large coefficients. So overfitting is still not avoided in this approach. We need something to do something more. And here comes this Bayesian approach. The idea of this Bayesian approach is such that we allow for parameters of our fitting function to be random as well. So we build so-called posterior distribution, which would give us eventually the probability distribution of finding our parameters such that they would fit the training set best. It is based as a product of a prior distribution, which depends entirely only on parameters, and it is given by this Gaussian function, multidimensional Gaussian function, and contains an additional parameter alpha. So this prior distribution is a probability to have a certain value of these parameters of our problem, times a conditional probability that given this particular set, W and alpha, what is the probability to have the best fit to the training set? And this is the likelihood probability we just considered before. So the posterior distribution, the total distribution of having the parameters which satisfy best the training set is given as a product of the two, the prior and the likelihood. And this is basically a product of two Gaussians. And this product, probability times the conditional probability, it is basically coming from the probability theory. So, in order to maximize this posterior distribution, which would give us the best fit of the best choice of the parameters, which would fit best the training set, we again calculate the logarithm of it and then maximize what comes out of the logarithm. And you can see here in red, this is what we had before in our regularization method, but we have here also some additional terms. So if we now maximize this expression with respect to the choice of our parameters, W and alpha, for W parameters, we will have to minimize that expression. It is exactly as I said in the regularization method, because in the regularization method, exactly what we have used. And you see, lambda in the regularization method appears to be this alpha of the prior distribution. By choosing this alpha properly, we would be able to avoid overfitting problem. So calculating the maximum of the posterior distribution is equivalent to using the regularization in the least square method. And the prior distribution in the posterior, it creates a particular constraints for the parameters W here, But in the method so far, we've used the maximum. So we obtained the particular value for the parameters, and this is manifested itself in finding the minimum of this expression, and therefore we will get a particular expression for the parameter, a particular discrete set of these parameters. In the Bayesian approach, however, we do something different. What we do instead, we allow all possible parameters, and instead we calculate the convolution of the posterior distribution with a particular set of parameters W, and the Gaussian corresponding to this particular set of the parameters, to choose, to predict a particular value of y given a value of x. And that value of x will obviously be outside the fitting set. And we integrate over all possible values of the parameters. So you see, in this case, we do not stick to a particular value of the parameters. We actually allow all of them to be used. And this formula is basically a formula of the sum and the product of probabilities. First of all, we sum over all probabilities because we integrate over W. On the other hand, for each particular W, we have a certain probability for it to be, and this would be a Gaussian for a certain prediction y at the given x, given these values of the parameters W. So this is a conditional probability. So this is a prediction, and one can show that because both of these probabilities are actually Gaussians, so this is multivariate Gaussian, this is one-dimensional Gaussian, you can integrate over all values of the parameters. You can perform this integration analytically and then define and calculate the final distribution, which again will be Gaussian with a particular dispersion and the particular mean. And in fact, it appears that the mean of that final prediction distribution would be identical to the mean obtained by maximizing the posteriori distribution. However, an additional advantage of using this Bayesian approach is that you can give the bounds to the predicted value y for the given x. You can say, for example, I get this y for the given x with confidence 60% or 70% or 90%. So you can actually calculate this because you get a dispersion. You have the full distribution, and therefore you have a dispersion coming with it. There will be a number of problems to illustrate all this, and also I will ask you to write a few little software, little codes for you to try these different methods.